and I'm now doing the opponents on problem number 7, cup drum. But just outline of the presentation, the proton had a very nice structure, and included, of course, the theoretical approach, the blade vibration of the cup, and of course, so the eigenfrequency of it, the standing waves that are produced inside the cup, as well as the damping and the pitch dropping effect. In his experimental observations, he had a very nice setup, and he could even give us some sound samples to get an idea what the sound is actually about. He had added a very nice method of frequency measurement, and at the end, in his comparison, he shows amplitude versus frequency, and he compared his results with the cup above the water and the cup under the water. Well, the good points of the presentation were that the very distance from the water above or below the water was quite a variation. They even compared with wavelength and frequency, and so even they could give us a relation between the pressure, which is deformating the cup, and the amplitude of the sound. The experiments included a different range from in terms of distance above the water, and even different frequencies, the different harmonics. But there were some missing points in our opinion. They could have actually experiments done with other materials, so the elasticity of the cup could be influenced by this way, and of course, so the eigenfrequency of the cup would have changed, which is a very fundamental fact for this problem effect. There were some measurement errors, and actually we cannot be so sure if the measurement is just has a very big failure or the theory is actually wrong. In these experiments, there were this is caused by the damping through the cup holding, of course. The way of tapping wasn't actually explained. This in discussion, and the position of the microphone is very important, but we will discuss it later on. Now I want the reporter to start the discussion, please. These are my points. Well,
okay, so the discussion starts with 10 points.
Actually, what is happening actually if you bang on this drum? Now? What is happening?
Right now, if you tap it like this, above water, there's a combination of the plate frequency as well as the combination of the standing waves that exist inside.
Yeah, but how do we get actually?
Frequencies that are explained in my presentation. So yes, thanks for that point.
And what do you think if there's water now here?
Okay.
What is the critical parameter for the reflection for the waves backwards?
Alright. The reason why
they have standing waves, they must somehow get back. Why don't they just add the cup if you have nothing under the cup? Why don't they just get through the cup and over here?
Alright, let me show you a picture here. He asked me the question of whether I consider the effects of the reflected sound. Now, if you want to consider a reflected sound, we need to firstly understand the basic principles of why reflection occurs. And the reason is, as you probably also know, is because of the difference in the acoustic impedance of the sound propagating underneath water when it's above water. In the case of when the cup is held above water but close to the surface, yes indeed there will be an acoustic difference existing there, but also there will be some forms of sound that transgress into the regions of water. There will be some reflected, but in order to analyze the cases of reflecting sounds, firstly it's not a dominant sound because the standing waves are the main points.
I have one point. If you just like again, what does change actually if you hit the cup right here and the middle here?
Changes with different hitting locations.
Let's have a look.
Alright, I can explain that with my theory as well.
Because with the elasticity and the whole materials of the cup.
Right. If you vary the hitting location, what happens is that in the thin vibrational wave equation that I've shown before, I told you that the solutions would be in the form of a root of the Bessel function. Now if you hit it in other locations other than the exact centrical axis, what happens is that other mode frequencies occur from different solutions of the Bessel function. When you hit it in the middle, that's the fundamental frequency that I defined.
Two other things. Imagine this obvious correction that the wavelength actually is a bit longer than the length of the cup, isn't it?
Yes, it is. That's the end correction.
What's actually your opinion about if we just get near to the surface within this obvious correction? The wavelength should actually be shortened, isn't it?
The wavelength should be increased because sound velocity increases a lot.
If we just come nearer, and the wavelength actually is actually longer than this, and now we approach the surface, the wavelength should actually be shortened because we have no place for it, isn't it?
All right. The reason why you think that there is no place for it, I think, is because you believe that this wavelength, this sound propagation, 100% reflects off the surface. But in reality, that's not really the case. There are proportions of sound that reflect, but there are also proportions of sound that transgress.
Can you maybe explain this nearer?
Huh?
Can you maybe explain this nearer? You make everybody understand?
Yes. The pitch sharpening effect that I explained is when a sound propagates from different materials and different mediums, there's a difference in the acoustic impedance, which you can easily understand as a form of resistance to an electric current. Now, because of this difference in the acoustic impedance, there are some portions of that initial sound propagation that reflect off the surface, but some actually transgress through it. Now, if you look at the components that transgress through it, the wavelength increases, and that's why the pitch drops.
Yeah, okay. What actually the crucial points in your measurement? Actually, did you have some system or some reproducible way of hitting the drum?
All right, I'll show you how I...
A very crucial point.
Alright, so the tapping method is firstly composing of a tapping machine that I built out of a science kit. And this is powered by a power amplifier and a constant speed velocity motor. So the frequency of the tapping is kept at constant with the same force. The location was exactly in the centrical axis I calculated with measurements.
Okay, well, more points. How can you explain or how do you calculate the frequency of water? First, we have something with water, and then oscillate, you have of course something vibrations or oscillations in the water. Did you calculate this in some way?
Alright.
What would you say?
The oscillations in water occur both when the cup is substantially close enough to the water surface, and this is because of the fact that the water weight, sound propagation, and the pressure differences also hit the water surface, but also the water vibrations get even bigger when it's submerged underwater.